This is the first in a series of videos that are going to be all about limits. Limit proofs, limit properties, limit applications. This video specifically will serve as an introduction to kind of get everyone up to speed. So we're going to go over what exactly a limit is, and we're going to use our intuition to determine what the limit of a function is by looking at the graph of that function. Now, I'm not going to go into a whole lot of detail about what exactly a function is, but I do want to talk about functions a little bit because they are important to what we are going to do. So the main idea with a function is that they take an input. We can call that input x. And that input gets mapped to some other value, f of x. And often f of x is a shorthand for the function itself. So for example, let's say x equals 2. Then that would get mapped to f of 2. And as long as you're using the same function, if you plug in x equals 2 into your function, you will always get that same f of 2. So limits work a little bit differently. Instead of using exact values, they kind of see, well, what if we're close to a certain value? So let's say we have the limit as x approaches 2 of f of x. So x approaches 2 of our function f of x. And what does that mean, right? It's kind of communicating a different idea. Sometimes it will be the same thing as f of 2. But what it means is that we look at the behavior of our function f of x as the value of x is very close to 2. And we try to deduce from that behavior what f of 2 would be if the function continues acting the way it was. But yeah, so the limit looks at values of x that are very close to what x is approaching. So in this case, 2, we might look at like f of 1.99 or f of 2.01. And for example, let's say f of 1.99, excuse my handwriting, let's say that's equal to 3. And f of 2.01 is also equal to 3. Well, we might say that the limit as x approaches 2 at f of x is also equal to 3. This is just an example. This is a rough idea. This wouldn't be how you would exactly determine it. But let's say you did this, and the closer and closer you got to values of 2, it was still equal to 3. Then you would say, well, yeah, well, it seems like if we were to plug in 2 to f of x, surely we would get out 3 as our output. Whether or not that's the case, we don't know. In some cases, it is the same. So finding the limit would be computationally the same method as plugging in 2. But what I would argue is more interesting are the cases where it is not. And we are going to look at some of those cases in an example. All right, so here's a graph that I just drew. And before we start looking at limits, let's just quickly go over the behavior. We see it kind of flattens out a little bit. It decreases like by a lot, and then it jumps all the way up here. It is not continuous at this point, so there's no value. This isn't a value, right? That's a hole. And then it decreases. And then right here, it jumps, and then it jumps back down. So just when x equals 1, it does that jump there. And then it increases some more, and then it increases a lot. That's just a vague idea. Now let's look at some limits. So let's start with our example. the limit as x approaches 2 of f of x. So we can use what we've learned about limits when the values of x are really close to 2, so right here and right here, we have values that are really close to 1.5. And in this case, right, this happens to be equal to f of 2, right? Because we see that our function is continuous at that point. And visually, we can see that it's getting closer and closer to this y value of 1.5. So the limit as x approaches 2 of f of x is 1.5. All right. What about the limit as x approaches 1? This is a more interesting case. So we see that when x equals 1, our function is at this dot right here. But that actually doesn't matter when we're figuring out what the limit is. Again, it's this idea of behavior, right? That we look at the values that are really close to 1, right? So 0.99 or 1.01. And we see that they're really close. The output is really close to -1. And so in this case, what we say is the limit as x approaches 1 of f of x is equal to -1. And in this case, it is not equal to f of 1, right? This is not equal to f of 1. So that's something important to know. Now, let's look at the limit as x approaches -1 of f of x. I'm going to write that up here. Okay. So what does that equal? Let's look at values of x that are really close to -1. So, okay. So -0.99, it looks like maybe it's getting close to 1.5. But like -1.01 is really small. So because if we look at values that are larger than -1 and values that are smaller than -1, and that behavior looks different, we cannot deduce what f of -1 would be just from what the graph looks like. We cannot come up with this hypothetical value. And so we say that this limit does not exist. And DNE is often an abbreviation for that. Okay, but fear not, because what we can do is we can break this up into two cases. Like I said, we were comparing values that were greater than -1, but also values that were less than -1, right? And so really what we can do is we can see, well, how about the limit as x approaches -1 from the right of f of x, and the limit as x approaches -1 from the left of f of x. So this plus, right, kind of implies from the right, and the minus implies from the left. Actually, I'm going to rewrite them so that they're a little bigger. All right. So hopefully that gives a better look. So let's look at values from the right. So values of x that are bigger than -1, but are still really close to -1, right? Like -0.99, like I said. So we kind of look right here, and it looks like y would equal 1.5. So we say, as it's approaching from the right, that limit is 1.5. So now we look at values approaching from the left. And this is an interesting case because the closer and closer we get to -1, it looks like it's just getting smaller and smaller and smaller. That there's not really going to be a value it looks like -1 would be if we were just looking at values from the left. But it looks like it's going to be really large in magnitude and negative. So we say then, in this case, that the limit as x approaches -1 from the left of f of x is equal to -infinity. Now, the next type of limit we are going to look at, which I've written over here, is the limit as x approaches -infinity of f of x. So we look at our function, and we look at the smallest possible x values, right? So ones that are large in magnitude, but also negative. So really far to the left on the x-axis. And so we see that there's this dotted line approximately where y equals 2. And we see that this graph is increasing up to that line. And this dotted line kind of implies that it doesn't cross that line. So what we're going to see is if we were to keep going left, is this would be increasing, but it would never cross y equals 2. It would never be greater than 2 if we keep getting smaller. So in this case, we say that the limit as x approaches -infinity of f of x is equal to 2. And now there's one more limit we are going to go over. This is the limit as x approaches infinity of f of x. So we look at the largest possible values of x, go to the rightmost on the x-axis, and we see what happens to our function. And so we look. We see x is getting really big, and it looks like our function is just going to keep increasing, and that there's not really a bound that it's going to increase to. So we say that the limit as x approaches infinity of f of x is equal to infinity. And like I said, for these limits, we just used kind of rough ideas, kind of saying, oh, well, it looks like it is going to be this. In future episodes, we are going to find a more rigorous, a more exact definition of what these limits mean, starting with this one. The limit as x approaches infinity of f of x equals infinity. And we will see, well, how exactly do we show and describe the idea that this will just keep increasing? That is it for today's video. If you have any questions, please leave a comment down below. And thank you very much for watching.